Get a little bit more difficult than nomenclature, though. With nomenclature, how many rules do we have? For binary covalent compounds, there is one set of rules. For binary ionic compounds, there is one set of rules. For Lewis structures, okay? Ultimately, all we're trying to do with Lewis structures is get a standard consistent structure. How do we go about getting that standard consistent structure? Everybody's got their own method. The textbook lists one. I've got another. I've seen other instructors come up with other ones. The rules that I've given here, I think, help facilitate a better understanding of how the structures work and ultimately really help out with that second to last concept, looking at resonance. Okay. And another thing that we'll go ahead and eliminate, we won't worry about assigning non-zero formal charges to atoms. So you don't have to worry about step 7 at all. Okay? If you have to move into organic chemistry, there's two really big topics that you have to get out of Lewis structures. Number one, resonance. I'm teaching second semester organic chemistry right now. The biggest weakness that my students currently have is resonance. Why is it such a weakness? Move into organic chemistry. The answer to 70 to 80% of the questions asked in organic chemistry, when you're asked to explain something, all you need to do is write resonance or say resonance. You have the answer. The other 30% of the time, you say size. If you're still wrong, well then you actually have to know what's going on. Okay? But resonance and size describe everything, okay, in organic chemistry. So it's a hugely important topic. So we'll see it in 130. If you jump straight into the fundamental organic chemistry, you'll see it show up in 230. If you take 151, you'll see it show up in 151. And you'll see it again when you get into the full organic sequence. So it's an incredibly important topic. The rules that I've outlined help facilitate and get you to the point where you can see that there is resonance. If you go a different method, you may not see those resonance structures appear. Yes.
What is that?
We'll talk about what resonance is when we get to it. Yeah. Okay. Last one, assigning all formal charges to atoms. Okay. You will have to do step 7 with a slight change. We won't do it per atom. We'll do it per molecule. Okay. So if your molecule is charged, you would see that where? Okay. In your structure, you would put brackets around it, and you would put the charge where? Upper right-hand corner. In the formula, where would you see that charge? It's in the same place. Upper right-hand corner. Okay? So, as far as our general rules go, you need to figure out how many electrons need to go into your structure. Since we're looking at bonding, they need to be the valence electrons. So you'll count the valence electrons for each and every atom. You then also have to account for charges. If it's positively charged, what had to happen? How do we get a positive charged atom? You had to lose an electron. How do you get a negatively charged atom? You gain an electron. All right, we'll look at what that gain and lose mean in a little bit. You'll then go through, decide on a central atom. That central atom needs to act as a connector or bridge. So you will find when you go through and start to work multiple problems that there are certain atoms that just do not work well as central atoms. Hydrogen is awful as a central atom because it only has 2 electrons, or maximum of 2 electrons. How many electrons do we need in a bond? In a bond, it's 2 electrons in a bond. If hydrogen can only have 2 electrons around it, how many bonds can it have? Only 1. Okay? The other one, though it has exceptions, most times your halogens will only form 1 bond. Okay? There are exceptions to that when we bind them to oxygen, but primarily your halogens will only pick up 1 bond. Okay? So you'll put your connector or bridge atom down and then scatter the other atoms around it. You can then start adding electrons in pairs to the most electronegative atom first. What is electronegativity? Define it. Okay. Very, very close. What I heard was the ability to hold on to electrons or attract electrons. Close, but not perfect. There's a big, big distinction between electronegativity and electron affinity. What you guys just told me was the electron affinity. What is electronegativity? The ability to attract a very particular type of electron.
Valence.
Take it a little bit further, bonding electrons. Okay, the ability to grab bonding electrons. When we're drawing out a structure, what are we trying to determine? The bonds that hold that structure together. So where should we put our electrons? Around the most electronegative element first, because it wants to hold the bonding electrons. That's why it's the most electronegative. All right? We'll add those electrons in pairs until we satisfy the octet. Okay, the octet is coming from your noble gases. How many valence electrons do your noble gases have? Did I hear all of them from outside? Okay, 8. How do we know they have 8 valence electrons? We look at their highest energy level. Okay, let's pick argon. Highest energy level is our third energy level. 2s electrons. And 1, 2, 3, 4, 5, 6p. Okay. Interesting little simplification here. What if we jump to, say, krypton or xenon or cadmium? We shift an extra row down in our periodic table, and now we bring in d electrons. Okay. Does that change the bonding ability? Absolutely. Do you need to worry about it? Absolutely not. Okay. Focus only on your noble gas rule. You're trying to get 8 electrons around an individual atom. Okay. I haven't seen any exceptions show up yet to that, so we won't worry about it in this class. You'll have to worry about it in 151. Okay. You'll then continue to add your electrons until you've accounted for the total count, so what you did in number 1. Okay. At that point, we can go through and start to do some simplifications. Anywhere that we have a pair of electrons between atoms, we can turn into a line connecting those two atoms or bridging them. What do I mean by between? Okay, Lindsay, can I get you to raise your hand? What students are between me and Lindsay right now? Okay. Are anybody on my left between me and Lindsay right now? Lindsay and I? No. Okay. Justin, right? Justin, can I get you to raise your hand now so everybody knows you? Is Justin between me and Lindsay? Lindsay and I? No. The only students between Lindsay and I are run right directly through the middle of us. Okay? What we'll do is convert those to lines, and then we want to evaluate our octets. Make sure every atom has its octet satisfied. If it does not have its octet satisfied, we need to make sure it gets those electrons to reach the 8 electrons around it. To do that, we will move a non-bonding pair of electrons, so one that hasn't been converted into a line, and we will move that pair of electrons to now being between the atoms. Well, if they're now between the atoms, what can we do to that pair of electrons? Turn it into another line. How many lines would we have between those atoms now? 2. What kind of bond do we have there? A double bond, because there are 2 bonds there. Okay? Next issue is resonance. This one becomes tricky. We will look at an example. I'll probably jump straight to the resonance example. Okay? What if there are multiple non-bonding pairs that you could move in? Okay? Well, if there's multiple different options, each of them equally possible, all of them have to contribute to it. Well, if they all contribute, we have too many electrons around our central atom, so that would be bad. So what do we have to do? You draw multiple structures. If you have 3 possible structures for resonance and you draw 1 on the exam, how many points can you expect to get? 1/3 of the points. Ultimately, that's failing, right? Okay. Resonance requires that you draw all the structures that equally represent it. Okay. Then the last one would be assigning your formal charges to the molecule. To do that, how do we learn to do that? Where do you always specify charge? Upper right-hand corner. since we want to make sure that that charge is now saying it's anywhere within our structure, we usually put brackets around our structure to specify that. Okay? Questions about the rules? I know we aren't looking at an example yet, but maybe we can get some clarification here.
When I was during the lab,
Uh-huh.
some of the, like ammonia, for example, the NH4,
Uh-huh.
sometimes they required brackets and sometimes it didn't.
It always requires brackets.
Is that only when it's like 2 of the NH4? Or is it always, like, even if it's only one NH4? You know what I'm saying?
You're looking at two different things.
Okay.
What you're talking about there is nomenclature
Okay.
to specify how many of that molecule are present. We aren't looking at nomenclature here. We're looking at what is the structure of the ammonia ion, or ammonium ion. Okay? So the structure is vastly simplified over nomenclature. We don't have to stress as much about it because it's just looking at one thing and not how 6 or 7 different things interact with each other. That was a bit dramatic. We won't see 6 or 7 different things. All right? Stay. Okay, so, or was there another question on that? Sorry.
Well, can you look at an example of one that has like multiple?
Exactly what we're going to work on. Okay, CH4 and ammonium, NH4 plus. Do we need to see those examples? So, vague head shake, yes. So we'll go ahead and draw those out real quickly. I'm going to do the NH4 plus because I think that's a little more challenging, and we'll do the CH4 in a little bit. Where do we start? Rule number 1. Valence electrons. So nitrogen brings in how many valence electrons? 5 valence electrons. Remember how we talked about electron configurations? You need to be able to identify the valence electrons. Okay. So we gave you the rule on what you needed. What do you need that rule for? Drawing Lewis structures. You have to apply that knowledge. So there's a lot of basic memorization stuff that was in that last exam that you will need to carry over to the new material. How many electrons does a hydrogen have? How many hydrogens are there? 4. There's 2 ways that we can go about doing this. We can count the valence electrons for every atom. So hydrogen has 1. The next hydrogen has 1. The next hydrogen has 1. Next hydrogen has 1. That works. I can accept that. Or 5 plus the number of electrons it brings in times the number of them. Okay? So what we've accounted for now are the electrons from our nitrogen and the electrons from our hydrogen. Our rule number 1 is total valence electrons on our atoms and charges. What is the charge in this case? +1. How do we get a positive charge on anything in chemistry? It must lose an electron. What is the mathematical symbol for lose? Minus. Okay. Where this can become a bit tricky with notation is that in this case we're just going to say -1. Okay. That accounts now for our charge. We total this up and what do we get? 8 electrons need to go into the structure. How does losing 1 give us a plus charge? So let's go back to that. If we ignore the charge, if we assume there's no positive charge, what would our charge be?
We have 1 extra.
0, right? If we need to get to a positive charge, okay, what can we add or subtract? Okay, what's the only thing we can add or subtract from an atom? Electrons. What's the charge on an electron? -1. What mathematically do we need to do in there to get a positive answer? You must subtract. Okay? What does subtraction mean? Lose the -1 was an electron. So to get a positive charge, what do you have to do? Lose electrons. How do you get a negative charge? Now we'd have to go through and add. What does that mean in English? Oh, never mind. You said that. It's been a long day for me too. Adding an electron. Mathematically, we're looking at the plus sign. Okay? I noticed there was some confusion with that. Okay? Now that we have our valence electron count, which was what? Now we can go through and start to build our structure. Our next step is to do what? Pick the central atom. It is usually the least electronegative. Which is more electronegative, hydrogen or nitrogen? What did I say? Least electronegative? Which is least electronegative? What is the most electronegative element on the periodic table? Fluorine. What is the least? All the way down to cesium. If we compare hydrogen to nitrogen, which one is closer to fluorine? Nitrogen, which means nitrogen should be more electronegative than hydrogen. So according to our rule, at least our abbreviated rule, what should our central atom be? The least electronegative would need to be hydrogen. What's the problem with hydrogen? It cannot bridge. Okay, so it's a general rule when we have other atoms there. We still have to have that bridging ability. So if hydrogen can't bridge, it cannot be the central atom, which means nitrogen ends up being our central atom. I remember it's usually, not always. Now what do we need to do? Scatter our hydrogens around. Why do I scatter it around in this general shape? There's two big reasons. What was Lewis's initial theory? The box. We simplified that into a square, right? Why would I put the hydrogens on those sides? To make a square. Okay, that's why we're trying to space it. We're also trying to put them as far away from each other as we can because why? They're going to repel each other. Hydrogen has, if we just look at its nucleus, is just a positive charge. That hydrogen is also a positive charge. What are those positive charges going to do? Get as far away as they can. Hi. Troy, do you still have your question?
Yeah, it's going to sound stupid, but
Nope.
how do you get 5 for nitrogen?
Counting valence electrons, we'll look at our energy level. What energy level is nitrogen in? Our energy level is also known as the row. What row is nitrogen in? The second row. We'll now count columns until we get to nitrogen. If we count, our first column is lithium 1, beryllium 2, boron 3, carbon 4, nitrogen 5. Okay? Comes back to the electron configuration, or we ignore the electron configuration and remember how to apply those. Okay? What do we do now? We're going to start adding electrons to the most electronegative. Which is our most electronegative atom? Our nitrogen is the most electronegative. We'll start putting the electrons in pairs, again on that kind of square face. How many electrons have we put in now? How many electrons should we put in? 8. Can we put any more electrons in? No. Okay, now that we've finished putting our electrons in, we'll convert our pairs into a line if they're between atoms. Where do we have electrons between atoms? I like that. Everywhere. What line should we use? Sometimes you'll see lines like this. I'm seeing some quizzical faces, so I like that. That technique is awful. Don't do that. Okay? What we're trying to represent is the bond connecting the atoms. Use your line as a bridge to connect your atoms. Okay? How many electrons are around each hydrogen? Where are those 2 electrons? In that bond. Okay, so we can count that line as a shared pair of electrons between nitrogen and hydrogen, which means hydrogen can count both those electrons. So it has 2. How about around the nitrogen? 8. Have we satisfied our octets? Yes. Hydrogen caps out at 2. Nitrogen caps out at 8. So we've satisfied our octets. Yes?
Is there some special
There is no special rule on it. I don't think you'll see it. Yeah. So the next level of difficulty with these would be moving up into organic chemistry, where you'll see some odd electrons, and you'll also see larger structures. No central atom. Okay? Those of you that have already taken the lab or have done most of that worksheet will notice that some of the lab questions, when it comes to Lewis structures, do a quite frankly awful job giving you examples, because they give you examples of structures that don't have central atoms. How do you go through and apply Lewis structure theory in its basic elements if you don't have a central atom? It becomes very challenging for you to figure out. Okay? A lot of those extra rules that you're thinking about, okay, or potentially considering for unpaired or a single electron, odd electrons, show up further on down the line, and we'd have to decide which atom would prefer to have the unpaired electron. So there's other rules that go into it in that case. You don't have to worry about that now. Okay. Other questions? Okay, so 7. Okay, looking at formal charge. The rule given there was when I assumed that we were looking at formal charges on atoms. Okay, turns out we aren't worrying about formal charges on atoms. What we're going to worry about are the formal charge on our molecules. Okay, our formal charge is shown. Let's pick orange. So rule 7. Where do we know what our formal charge is? How do we know what it is? We look at the top right of the formula that we were told to look at or make. What's our formal charge on this molecule? +1. What's the formal charge on our structure? It needs to be +1. Have we specified that it's +1 yet? Nope. How do we fix that? We can throw up the brackets. What color? And on the outside of that, we put our plus charge. Okay, questions about that? Okay, let's do a resonance example. Our resonance example is going to be the very last one on that list, our SO3. So, same rules as before. Where do we start? Count the valence electrons. How many electrons does sulfur bring in? 6. How many electrons does oxygen bring in? How many oxygens are there? What does this give us as a total? 6 times 3 plus 6 gives us 24 valence electrons. Okay. Which is our least electronegative element? Sulfur will be our least electronegative. Okay. Oxygen is closer to our fluorine. If we had to decide between oxygen and chlorine, that's a little bit more difficult. Oxygen in general, or is the second most electronegative element on the periodic table. How do I know that? I memorized it. Okay. So there are some basics of the electronegativity trends that you would, or some common things that you end up using again and again that you'd have to have memorized. I would probably tell you which one was the center, chlorine or oxygen. Okay? Or you would see it. If we did ClO4, what do you think our center atom would be? It's chlorine, because we've got 4 oxygens shared, 4 oxygens that we have to somehow put around a center atom. So we're going to try and go with the most symmetry. We'll put chlorine in the center, otherwise it's not symmetrical. And yes, I see you guys with a question.
Electronegativity go or increases you up 2, or is that?
It goes up 2, yeah.
Oh,
So
without having to memorize it, you would know that because
yeah.
I know it's so hard, like the 6 column.
It's easier to just say memorize, but yeah. Okay, so what did we say our center atom was? Sulfur. We now want to scatter our oxygens around the sulfur. Okay, how do we do that? There's a couple different methods. What if I did this? Is that equally valid? Yeah, absolutely equally valid. Is there a better way to scatter them?
Yeah.
What's that better way?
Triangle.
We want to go kind of in a triangle?
Triangle.
Triangular? Triangular shape. There we go. Why triangular? Symmetry. Okay, so symmetry is an argument. Looks better is the same argument. When we looked at our hydrogens, why did we space our hydrogens on the four sides? Because that got them all away from each other. If we did oxygen where we didn't put them in this trigonal shape, our oxygens would be pretty close to that top center one. Okay, so we're trying to give them as much space as possible. This starts to lead into the next topic, looking at valence shell electron pair repulsion theory. Okay? So what's our next step? Put in the valence electrons, right? Where do we start adding our electrons? Okay. Two theories on this. If you pay attention to the book, it says put it around the central atom. That's awful. Probably the worst thing you could go through and do as far as understanding resonance. You should put it around the most electronegative atom. Our most electronegative atom is oxygen. Which oxygen is the most electronegative? They're all the same, so does it matter where you start? No. So go ahead and just do it. Okay. You'll notice that I will skew my box now on that oxygen. Why should I skew it a little bit? I'm trying to get the electrons matching up with that sulfur atom. Okay. If you don't organize it in this trigonal fashion and you go back to the square fashion, that's fine. Keep it in that square fashion. We've now put in 8 electrons. Have we accounted for them all? Nope. So what do we do? Go to the next oxygen. Same deal. 8 electrons. Next oxygen, 8 electrons. How many electrons have we now put into the structure? 24. Okay. So what does that mean? Stop putting in electrons. Now go through and convert pairs of electrons into a line when they are between atoms. What electrons are between atoms? Okay. We now have our basic shape or basic skeleton to our structure. The next rule is to make sure we satisfy the octet. Take a look at the oxygens. How many electrons are around each oxygen? 8 electrons. We see 6 electrons that are not in bonds. And then we see the red line signifying our bond. How many electrons made up that line? 2. Shared between both of them, our oxygen has 8 electrons. All oxygens have 8 electrons in this structure. Fantastic, awesome, good. Sulfur. Sulfur has 6 electrons around it. How many electrons does it need? And careful. 8. What is the rule? Satisfy the octet. Okay? For those of you saying 6, that is a common mistake with this. What are you thinking? The valence shell. We don't care about how many electrons are supposed to go into its valence. We care about the octet. Okay? Sulfur needs 8 electrons around it. So how do we get 8 electrons around sulfur? Okay, what we'll need to do is move electrons. Move a pair of electrons now between the sulfur and one of the oxygens, or one of our possible oxygens. Okay, which oxygen do I take electrons from? Doesn't matter. So let's take it from the top. Okay, that sounded kind of funny. So if we were going to look at this in organic chemistry, we would show, somebody laughed. We could take the electrons and we would show that they move into the bond. So we could use that arrow. For what you guys need, all you need is the eraser. And we turn it into this. And we now have the double bond. Did we have to take it from the top oxygen?
No.
No. Okay. I'll address your question first.
Can you take one from one side and one from the other side?
If you take them one from one, we leave unpaired electrons. We don't want unpaired electrons. Everything should be paired. Okay. And you were saying on the same oxygen? One from the same oxygen? Yeah, we want to leave them in pairs. Okay. Did I have to take them from the top oxygen? No. I could have taken them from one of the side oxygens. And since you got to draw all your stupid lone pairs, I'll do it too.
You're not going to knock off if we don't do it in triangular format, right?
No. You do not need to be triangular. What is the difference between these three structures? Okay. Kind of, sort of, nothing. Okay. And what do I mean by kind of, sort of? As far as energy goes, we've got two oxygens that have 3 pairs of electrons on each of them. We've got an oxygen that has 2 lone pairs and a double bond in each case. Okay. So all of these are equivalent. We could have used any one of these. Now's where it gets a bit tricky. What we're going to do when we think about resonance is we will now freeze the position. Okay? So when I look at the oxygen on the right, I'm going to call that the right oxygen, the left oxygen, and the top oxygen. To get to the next structure, where's my right oxygen? That is on the right, isn't it? Yeah, okay. It's still on the right. The left, the top. What are you guys doing when you're saying how it switched to a different position? You've rotated the structure. When looking at resonance, we do not move the structure. It is now pinned. Okay? So our right oxygen is always the right oxygen. Why is this important? What is the difference between these structures? Is there any difference?
Yeah.
As far as energy goes, no. They're all the same energy. Which means if I ask you to draw the Lewis structure for SO3, what answer do you give me? All of them. All 3. Why? All of them are the exact same energy, which means you have to specify all of them because they all look different too, because of where that double bond is. Okay? So with resonance, you don't get one answer anymore. You can get 3. You can get 6 or 7 for that matter. Okay? Sometimes it'll be nice and you only have to deal with 1. Okay? We will make this more difficult in organic chemistry, but at this point, we can stick with this. So why does my method help show resonance? Most people go through and say, oh, there has to be a double bond. So they draw the double bond starting with the sulfur. What's the issue with that? Do you now see that all of those oxygens could have just as equally given you electrons? Some people see it, yes. Most people don't see those options. If you go through and follow these steps and you get to that point where that sulfur is now missing electrons, you have the option to pull from all possible oxygens. You see that option in theory now, and that means you now have to draw them all. Whereas if you start with the double bond, you typically don't see that there are multiple ways to get that pair of electrons in there. Okay? Resonance takes lots of practice. Remember, second semester organic chemistry, they have gone through 4 more semesters of chemistry, and they are still, just in case they listen to this, god-awful at it. Okay? So it takes practice, takes a little bit of work, but it will get you there eventually. So Thor, then Lindsay.
So if you say you draw the Lewis structure, we have to automatically assume it includes resonance then?
Yes.
That's exactly my question. So you just know that SO3 is 3 different possible shapes?
So you don't have to know that SO3 is 3 different possible shapes. As you start to draw your first Lewis structure, you get to, and we'll have to erase back, you would get to this point, okay, with our purple, red, and blue one now. You would get to this point and say, oh crap, I've got 3 possible oxygens that can donate electrons. That means I need to draw 3 structures. Okay? Do you have to go through each of the individual steps to draw those extra structures? No. because all you're doing is just shifting it off of this one. So you can get away with now shortcutting the rest of those steps once you got the basic skeleton down. I won't do another example because of time. I think we're done at 30 or 40? 40. I'll do another example on Tuesday. I do want to talk about valence shell stuff. Yeah.
Then for hydroxide,
Yep.
you'd have to do 4 with resonance because the H can be on all sides of the oxygen.
Once you pin your structure, you're looking at how you shift the electrons within the structure. Do the electrons change with hydroxide? No. So it's not looking at how you can rotate an individual structure, but once you've got the basic skeleton down. So it's ultimately double bonds. Resonance is all about how you make the double bond, not the single bond.
So resonance is like you have to draw the possibility of
All the possibilities, yeah. In this case, it's 3. It could be as few as 2. It could be as many as probably 10. All right. Yeah.
So repeat what you said about the resonance, only applying to the double bonds?
Resonance will only apply to double bonds. If you have double bonds in your structure, that should be a tip-off that you might have resonance. It's not a guarantee, but you might have resonance if you have a double bond in your structure. Okay. If you have no double bonds, you're all single bonds, will you have resonance? No. Okay. Other questions on it? Any multiple bond. Other questions? Okay. We're going to finish up a little bit more our coordinate covalent bonds. I don't want to talk too much on this, but if we take a look at ozone in this case, we can take a molecule of O2, and they attempted to show the Lewis structure here. O2 is nice and happy with what kind of a bond between the 2 oxygens? How do you know it's a double bond? Every pair of electrons we can turn into a line. There's our double bond. Okay. If we now bring in O3, we bring in an extra oxygen. Oxygen has 2 electrons, or a 2-electron hole in it. What can we put into a 2-electron hole? 2 electrons. Okay. Remember, your holes can only hold electrons. So if we've got a hole, we can slide 2 electrons into it, and what we end up with is what's known as a coordinate covalent bond. Okay? Typically, the coordinate covalent bonds apply with your metals, not so much with something like oxygen, but it's a reasonable example for showing that gap. Okay? So if you're putting together a structure with these kind of things, you would probably see it start with this example, say O2 plus this. What's the bond formed when we move to O3? Okay, what is the bond that's formed? Covalent, polar covalent, ionic, coordinate covalent. Coordinate covalent. Okay, that's about the extent of the question that I would ask. Identify that that's a coordinate covalent bond. Okay, it's a little bit different than the other ones just because of how the electrons are shared. Okay. Hydrogen bonding is probably one of the most easily confused concepts. It's called hydrogen bond, right? Is that a bond? What is a bond? It's all about sharing of electrons. Do we share electrons in hydrogen bonding? No. There is no sharing of electrons in hydrogen bonding. Why do we call it hydrogen bonding then? Because some old stupid chemist decided to call it bonding and then confuse everybody thereafter. Hydrogen bonding is a force. It's an attractive force, but it's not a bond. Okay? That's because it's too weak of an attractive force. Hydrogen bonding is or let's call it something else. Hydrogen not bonding. That's horrible. Hydrogen not bonding is one of probably the most important intermolecular forces on the planet because we're looking at how water organizes. Why would that be important on our planet? There's a lot of water. What does all of our life currently have as a solvent? Water. What's going to determine how our proteins interact with each other or how they interact with their environment? Water. It all comes back to hydrogen bonding. Okay? When can you have a hydrogen not bond? Okay? First rule, what do you think you need to have? You need to have a hydrogen. Okay? Next rule is it needs to interact with something. So here's our dotted line showing that interaction. Okay? For it to be a hydrogen bond, what we're trying to do is generate something very, very polar, approaching an ionic bond. To do that, what partial charge does our hydrogen need to be? Partially positive. Why would it not be partially negative? How often is hydrogen negative? Very, very, very rarely. Okay? If it's going to have an interaction, what is that interaction going to be with? Something that's negative or positive or neutral? Why should it be negative? We're trying to cancel out that charge. So whatever this atom is it needs to be partially negative. Okay? For hydrogen bonding to be such a big issue, it's really coming back to water as our primary example. So typically, you will see the example where we're bonding to oxygen or interacting with oxygen. Okay? How do we get the hydrogen to be partially positive? What does it need to be attached to? For instance, if I made it another hydrogen, would our hydrogen be partially positive? Why is it neutral? What type of bond is there between hydrogen and hydrogen? Nonpolar covalent. What partial charges show up on nonpolar covalent bonds? None. For it to be hydrogen bonding, it must be partially positive. It needs to be attached to an electronegative element. The general rule is it needs to be attached to oxygen, nitrogen, or fluorine. Why those three elements? What do oxygen, nitrogen, and fluorine have in common? They are the three most electronegative elements on the periodic table. They're going to be the ones that generate the largest partial positive charge on that hydrogen. Okay? What does that mean our partial negative can be? Oxygen, nitrogen, or fluorine. To have a hydrogen bond, all of these rules must be satisfied. If I drew this, is that a hydrogen bond? No, why not? Because it's carbon, not oxygen, nitrogen, or fluorine. Here's another fun question.
Those three words only?
Those three only. What is that? What is that interaction? That is equal sharing of electrons. We're looking at a nonpolar covalent bond that happens to be between carbon and hydrogen, not a hydrogen bond. Okay? I know, that was intentionally tricky. So watch out for that. It's nonpolar. Carbon and hydrogen is nonpolar. Okay? Questions about that? Okay. So, if we looked at the Lewis structure for CH4. Oh, looks like I still got 5 minutes. Lewis structure for CH4. Why did we organize the hydrogens the way we did? Try and get them as far away from each other as possible, balance it out, right? Okay. So Lewis theory does a good job of explaining this. We now want to push into 3 dimensions, which is the bane of all organic chemistry students, okay? Because very few people can see in 3 dimensions. Okay? So we look at that as a 3-dimensional artist person. We say, okay, all of those hydrogens are the same. A hydrogen is a hydrogen is a hydrogen, which means all of the bonds between the hydrogen and the carbons are also the same. Okay? Which means what bond angle should be between those? If I look at the bond angle here, what's that bond angle?
90 degrees.
The way it's drawn, we see 90 degrees. What is it over here? 90 degrees. Here? 90, 90 degrees. Okay. Those bond angles all need to be exactly the same. Why should they be exactly the same? Each of those hydrogens are equally repelling away from each other because they're all exactly the same. So on the surface, we might say this is an absolutely fine structure. There's another bond angle in here that we haven't specified. What is that bond angle? What's the bond angle there? 180. Are all of the hydrogens equally distant away from each other? No. If we take a look at our purple hydrogen, it is now 90 degrees away from our orange, but 180 degrees away from our blue. Lewis' theory works great to explain the bonding. It does not explain the three-dimensional structures. Okay? That is where valence shell electron pair repulsion theory comes into play. It says, okay, yes, we know what all our bonds are, but now what we have to do is explain what happens when we pull this out of the paper and put it into 3 dimensions. Okay? We need to essentially average out all of those angles. If we went through and did that, anybody know what shape you would get? A tetrahedron. If we take a look at CH4, this is what it looks like. It does not look like hydrogens going equally out each direction, or sorry, in a plane. How would we draw this? Particularly if I'm moving it, how would you draw it? Would you be able to draw that? No, what do you need? You need probably to stop moving, right? Okay, well, if we stop moving and now try and draw it, we'll pick probably the simplest way that we can orient that in space. So what I'm going to do is draw it where the plane of my paper, if I don't drop my expensive stuff, right through the middle, which means where my fingers are in the plane of the board, or the plane of my writing. The carbon atom is in the plane, and that last peg out there, as I pull some acrobatics, is also in the plane. How do I draw something that's in the plane? We just use a solid line. I rotated it. Is that right? Yeah, that's right. What about this atom? The one out here. Where is that? Okay, it's going to your left. I agree with that. What else can you tell me about it? Is it in the plane of the paper? No. Where is it coming? At you. How do we draw something coming out at you? It's a good example. It's usually fun to scare people. What happens to things when they come at you? They get bigger. You're welcome. So what we use is typically a wedge to show that it's coming out at you. What do we show for the atom that's not coming out at us? We got to try and show the reverse of it, but if we showed a wedge, now we get confused. So we come up with a new notation. Use a dotted line or a dashed line to show that it's going away. What we're now trying to do is draw in 3 dimensions on a 2-dimensional piece of paper. Not the easiest thing to do, okay, to represent that shape. Take a look at your valence shell theory. I know everybody's going to have a lab on it. We will discuss it in lab, and we'll look at it again briefly on Monday, as well as do another resonance example. If you want to jump ahead on what that resonance example will be, we will take a look at CO3 minus 2. Will be the example we'll start with on Monday. We'll finish up the valence shell electron pair repulsion, looking at shapes, and then we will continue on to the rest of the material, which is chapter 7.